Hello students, today the topic is diffraction. So I will discuss the basic phenomenon diffraction. Let us take an experiment before going to the definition of the diffraction. To illustrate what is diffraction, this is an experiment. This is called narrow slit experiment, because we have taken a narrow slit here. This is narrow, though it is seen wide because it is a schematic of the experiment. So we have a slit, the width of the slit is AB, and a parallel beam. It is illuminated by parallel beams. Parallel beams are coming. If we consider the rectilinear propagation of the wave, then parallel waves actually, if we consider the rectilinear propagation of the wave, then this is a screen XY, then the A prime B prime portion should be illuminated, and the other portion of the screen, that is A prime to X and B prime to Y, that part should be, these parts should be completely dark. But however, it is found that this is the intensity distribution curve. From this graph, it is seen that the intensity of the light, this part, in the part A prime B prime, which should be the enlightened part, in this part the intensity is maximum at the middle, and it decreases, but it enters in the geometrical shadow. That is, this part is illuminated, but the geometrical shadow part is also illuminated by a small intensity. So it is seen that the light bends around the edges of the slit. That means the light bends around the edges and comes to the geometrical shadow region. So as we say, that light bends around the edges of the slit and penetrates into the region of geometrical shadow. This phenomenon of light is termed as diffraction. Actually, this effect is general characteristics of waves phenomena occurring when a portion of wavefront, be it sound or a matter wave or light wave, when it is obstructed by obstructed in some way, it bends towards the geometrical shadow region. This is, and this phenomenon, diffraction phenomenon, can be easily seen in the case of water, in the case of water surface or sound waves. We can hear the sound of a man. Standing in one side of a wall, and we can hear the sound on the other side of the wall. This is because of the diffraction phenomenon of the sound. But in case of light, it is difficult to observe the diffraction phenomenon, because wavelength of light is very small compared to the wavelength of the water waves or sound waves. Let us take another experiment. Here we have a source S, and a disk AB is placed in the path of the light. So it is expected that on the screen, this is a screen, it is expected that on the screen a diameter of about, if we consider the rectilinear propagation, then the diameter of A prime B prime should be dark and the other part should be bright. But what we see in normal situation, it is not normal situation, it's a very small disk. So we see that the middle portion, that is at the center O, we see a bright ring, and then alternately bright and dark rings are visible. So this is, it shows that light bends around the edges of the disk, penetrating into the region of geometrical shadow. So the light bends towards the geometrical shadow. In course of encountering an obstacle, either transparent or opaque, a region of the wavefront is altered in amplitude or phase. Diffraction will occur. The various segments of the wavefront that propagate beyond the obstacle interfere, causing the particular energy distribution referred to as diffraction pattern, that is superposition of many waves. To understand the behavior of waves obstructed by any object or surface, we take an heuristic approach made by Huygens. We take this heuristic approach as it is difficult to apply the boundary conditions for the obstacle placed in front of a source. It is very difficult to calculate, so we take the heuristic approach of Huygens. What is that approach? As an initial approach to the problem, according to Huygens principle, every point on a propagating wavefront acts as the source of secondary wavelets, such that the wavefront at latter time is the envelope of these wavelets, and if the propagating wave has a frequency nu and is transmitted through a medium at a speed vt, then the secondary wavelets have the same frequency and speed. So this is a wavefront, and considered according to Huygens, all the points are though it has infinite number of sources, but it is not possible to draw infinite number of sources, so it is here we have drawn a finite number of sources. All the points on the wavefront acts like as the source of secondary wavelets, and after a later time, the envelope of all these wavefront is the represents the wavefront. If the medium is homogeneous, the wavelets may be constructed with finite radii, and if it is inhomogeneous, the wavelets must have infinitesimally small radii. You can see from the diagram. This technique ignores most of each secondary wavelets and consider only the portion common to the envelope. From the figure, it is clear that the major portion of the wavelets are not considered here. Only the common portion of the wavelets are considered as the envelope of the wavefront. Thus, Huygens principle is unable to account for the details of the diffraction process. Huygens principle is independent of any wavelength consideration. So, this difficulty was resolved by Fresnel in 1800s with his addition of the concept of interference with the Huygens principle. And on the latter time, Kirchhoff shows that the Huygens-Fresnel principle was a direct consequence of the differential wave equation. The Huygens-Fresnel principle states that every unobstructed point of a wavefront at a given instant serves as a source of spherical secondary wavelets with the same frequency as that of primary wave. The amplitude of the optical field at any point beyond is the superposition of all these wavelets considering their amplitude and phases. So here the amplitude and phases are also considered. This is the Huygens-Fresnel principle. So according to this principle, diffraction phenomena is divided into two groups: Fresnel class diffraction and Fraunhofer class diffraction. This is the schematic of the Fresnel class diffraction. In Fresnel class of diffraction, the screen and the source are at finite distance from the obstacle. This is the source, obstacle, and the screen. All are at finite distances. Actually, the source is at finite distance from the obstacle, and also the screen is at finite distance from the obstacle. Here, the wavefront incident on obstacle is either spherical or cylindrical. The secondary wavelets from different points of the obstacle are not in same phase, as because the wave front is spherical or cylindrical, the wave front reaching at the obstacle are not different for all the points on the wave front, so they are differing in phase. This is Fresnel class diffraction, and since the source is near to the obstacle or the screen is near to the obstacle, so it is termed as also near field diffraction. This is the schematic of Fraunhofer class diffraction. The source and the screen are effectively at infinity. This is a schematic, so this distance is effectively at infinity. This distance is at infinite, this is infinite distance, and this is also infinite distance. As these are infinite in distance, the incident wave front on the obstacle is plane. All points in the obstacle become a source of secondary wavelets simultaneously. Here all the points are acting as the source of secondary wavelets. The secondary wavelets starting from the obstacles are in phase, as the incident wave fronts are plane, so they are all in phase. And also the this distance is, since this distance is at infinity, so the beam the wave fronts reaching to the screen also, they are plane parallel, plane waves. Let us consider a point source S and a point of observation P, where this is an obstacle O, and let us first consider the L1 and L2 are, these lenses are not present here, so the waves are coming to the obstacle, both obstacle and also the beams waves of from the obstacle to the screen, they are taken as at effectively large distance, and so the waves that are reaching to the obstacles are plane waves, and also the waves reaching to the screen are also plane waves. The phase of each wave contributing at P due to difference in the path traversed, the path there is if we consider the point here or here or here, there is a path difference, so it is crucial to determine the resultant field at every point. Now if this distance is not far enough, or these distances are finite distances to obstacle to screen, or obstacles to source and obstacle to screen, if these are distances are finite distances, then we can say this is a Fresnel class diffraction. But each point on the aperture is to be visualized as a source of Huygens wavelet, and we should be little concerned about their relative strength. When S is nearby compared to the size of the aperture, a spherical wavefront will illuminate the whole. The distances from source to each point on the aperture will be different, and the strength of the electric field, which drops off inversely with the distance, will vary from point to point over the diffracting screen. And even if all the emitted waves from the obstacle are of same amplitude, if P is nearby, the waves converging on P are spherical and vary in amplitude, because of the different distances from various parts of the aperture to P. For P at infinity, that is in the case of Fraunhofer diffraction, if the system is at infinite distance and this system is at infinite distance, the waves arriving there will be planar, and we need not to worry about differences in field strength. So if it is finite distance, then the waves will be spherical. If it is infinite distance, the waves will be spherical, and we get the Fresnel class diffraction. And if the construction is such a way that this distance is infinite and this distance is also infinite, so we get the Fraunhofer type diffraction. And Fraunhofer diffraction occur at an aperture of greatest width A when r is greater than a square by lambda. R is the smaller the distance from the smaller between the two distances, S to O or O to screen. From the expression, it is clear that when r is infinity, the finite size of the aperture is of the little concern. Moreover, an increase in lambda clearly shifts the phenomenon towards the Fraunhofer class. A practical realization of the Fraunhofer condition, where both S and P are effectively at infinity, is achieved by using these two lenses L1 and L2. In that case, the source S, we have to put the source S at a distance at the focal plane of the lens L1, and the screen must be put on the focal plane of the lens L2, so that the waves that are coming from the source after the waves coming from the source becomes plane parallel after going through the lens, and after going through the lens L2, they converges to the point P or Q or any other point which is on the focal plane of L2. So this is the practical realization of Fraunhofer diffraction. So this is the introductory part of the diffraction. In the next class, I will discuss about the Fraunhofer diffraction. In this lecture, we have seen that the Fresnel diffraction is the diffraction pattern that we normally observe, but Fraunhofer diffraction is the special case of Fresnel diffraction. Though it is simpler in the calculation, so we will first go through the Fraunhofer diffraction, different cases of Fraunhofer diffraction, then we will move to the Fresnel type diffraction in the later discussions. Okay, thank you for watching.